Swayam Prabha. Digital India. Educated India.
So let's look at an hexatriene. That means now I am taking a 6 p orbitals. Obviously, I will have 6 molecular orbital coming up. So hopefully, I will be able to draw here. If it is smaller, please pardon me, because I have to draw 6 of them. Right, 6 are there. Right, so 6. 1, 2, 3, 4, 5, 6. So this is the third orbital. We'll place a node up accordingly so that the energies are higher. Okay. The fourth one, four, 5, and 6, and fifth one is here. When I keep going up, the size is coming smaller. Huh? The last one is here. Even for me, this board looks a little higher. Okay. So now, if we start for hexatriene, we have a 6 p orbital. I will have obviously 6 pi molecular orbitals. This is all only, I am not looking at sigma, I am only looking at a pi molecular orbitals. Remember, again and again, pi molecular orbital only what we are talking about. So the psi 1 will have 0 node. So this will be like this. The psi 2 will have a 1 node, that should be in then a material. So that way a symmetry point we say. A psi 3 will be 2 nodes. Once again like this. And here you will have 3 nodes. Okay. So you will have a psi 4. The next will be a psi 5, which is in 4 nodes. I am sorry, I should. Right, this way if you see, I will have psi 5, and the psi 6 will have 4 nodes, right? So in this case 5 node, I am sorry, 5 nodes, you are right. Psi 6 will have 5 nodes. So this is how you derive n pi molecular orbitals. So in this case, how many electrons we are going to see here? 6 electrons. So that means the psi 1 will have 2 electrons, psi 2 will have 2 electrons, psi 3 will have 2 electrons, psi 4 0, psi 5, psi 6, which is HOMO? Psi 3. Which is LUMO? Psi 4. Correct. So this is how we derive. So that means for an 4n system, and this is 4n plus 2 system, right? Let's generalize this, because I can go to an higher order as I told you. Let's generalize it how we will see it. Right. So this is at the ground state. In other words, under thermal condition. Okay. Under thermal condition, you don't have any excitation. This is normal. It will be the same here, or in the ground state as I talked about, right? Either of them. Okay. In a normal thermal condition, in a 4n system, the HOMO, because it's a unimolecular reaction I am talking about. If I look at a bimolecular reaction, I can talk about an HOMO of one unit and then LUMO of another unit. But this is being a unimolecular reaction, I have to have an electron. So that I have taken and only HOMO to represent the whole phenomena. That's that then the frontier molecular orbital. So I taken an HOMO alone. Now connect with the symmetry what I mentioned for an coordinate disk. Okay. So the HOMO of an 4n system in this case is sigma symmetric or sigma antisymmetric? This one, this is a HOMO, right? It is a sigma antisymmetric. Okay. In a thermal condition, a 4n system, a sigma antisymmetric, which means it has to go through Kahn rotation. That's all the point. Okay. This is sigma and antisymmetric. Under a thermal condition, it is this true, right? If a same thing when you look at an 4n plus 2 system and hexatriene like, this is a HOMO. What about this here? No, it is symmetric. I can have a plane here. I mean, planar symmetry means when I place, the sign of the lobes has to be same. I think I did not get that point. So, if I place here and mirror the sigma plane, here it is plus, this is minus. So, this is antisymmetric. There is no sigma plane in it. But here when it comes, the minus minus, plus plus and plus plus. So, there is a sigma plane. It is sigma asymmetric. Based on the discussion what we had before, you will realize that disk rotatory mode would give you a bonding if the HOMO is sigma symmetric. That's why, see, if you look at this, an internal one we need not worry about. What we worry about is only the terminal lobes. That's why I choose only terminal lobe to explain and Kahn and this. Here also is the same. When it is sigma symmetric, the terminal ones will have a same sign on the same side. Okay, and antisymmetric. Now, let us look at under photochemical condition. So, what you do? You give an photon energy, then what will happen? Exactly, you under photochemical condition, you would excite one of the electron from this to this. Don't worry about the spin of electron. Sir, it is in plus or minus, don't worry about it. I want to define a HOMO and LUMO only here. We are not worried about a spin. Okay. So, now because of photon energy I give, so I can kind of do this. Now, what happens? A HOMO and LUMO will remain the same or change? A change. Now, for this system which is HOMO, psi 3 is the HOMO, as psi 4 becomes a LUMO. Luckily, we need not worry about LUMO here because we are looking at an electrocyclic reaction. We only have to worry about a HOMO. Okay. So, here as we said, we need an Kahn rotation to do it. What about this? This psi 3 which is a HOMO under the photochemical condition, it has a sigma symmetry or it is sigma antisymmetric? Sigma symmetric, correct, right? So, you have a sigma plane here. So, this is sigma symmetric. So, if this sigma symmetric means a disrotation, perfect. Alright. Let us come to this again. The same here under the photochemical condition, right. So, we will have a bottom 2 has a 2, the next will have 2, then I will kind of excite 1. Now, HOMO becomes an psi 4 under photochemical condition. The HOMO which you consider is psi 4 here, LUMO is psi 5. When you come to an HOMO and photochemical condition, this, if you look at a sigma plane, this is exactly sigma antisymmetric. Okay. So, that would be, here it is, as we said, here it is previously it is this, here it will be Kahn, that is alpha. This is how one can kind of explain the behavior. We will come back to behavior again, like the selectivity what we mentioned, we will take these HOMOs and then we will explain further. But now I want to generalize this as a selection rule for an electrocyclic reaction. For electrocyclic reaction, how do we generalize this? So, you say a number of electrons involved, okay, that is one side, versus a reaction condition. Which is a thermal or a photochemical. So, beauty of this reaction is the same substrate, as I told you, can undergo reaction under both the conditions. That is the beauty here. Okay. So, now that means if my system is 4N, like what I mentioned here, like a butadiene, under thermal condition, Carnot rotation I have to consider. Under photochemical condition, this. And 4N plus 2, just a reverse. It is this and this is a Carnot. So, this is a selection rule. Okay. So, if you have to understand what kind of mode of cyclation you are going to perform, first thing is you need to check the number of electrons involved in your molecule in a reaction, in a polyene, what you are talking about, conjugated polyene. Remember, a conjugated polyene. By some means you have a skipped diene kind of systems, this will not undergo electrocyclic reaction. Remember, it has to be always a conjugated polyene only we have to consider in this case. Okay. If it involves a number of electron which is a 4N, then based on the condition you choose either a Carnot rotation or this rotation. Okay. If it is 4N plus 2, once again based on the condition you use this or Carnot. Okay. Now we are going to go back to the examples what I given you, two system which is butadiene and hexatriene with the same, both the terminals are E olefin which we talked about and E and Z which we given. Let us look at how the reaction occurs and whether the product what I mentioned is correct, or can we explain that by this way. Okay. So, now let us see that. So, we had the first case, we had this is an example we said, and we did, let us say thermal condition. What is the product we mentioned there? Thermal power. Trans. Okay. Now, what I supposed to do? I supposed to do a Carnot rotation. Which axis I am going to see? Generally, an axis is this carbon-carbon bond. Okay. So, consider that I am going to do both a clockwise. That means clockwise is this way, right. So, this is a clockwise I am going to do. So, if I do a clockwise like this, the methyl group which is away, right, this is how my alkene is. The thumb is an methyl group, for example. I am rotating clockwise. From here, I am rotating a clockwise. That means what is going to happen? The methyl group would go, when the bond is forming, the methyl group will go up. So, for if you consider this is once again I label this, sorry, 1, 2, 3, 4. For a atom which is fourth atom, the methyl group is just pointing outside because the diene which is considered as an outside. So, when you do a clockwise rotation, the methyl group will go up. For the one which is on the top, which is at the first carbon, the methyl group is again outside. Again, what I am doing is a clockwise only I am doing, right. Here also I am doing a clockwise. Then I have to further rotate it this way, it would go down. It's clear? That would give us a product which is, this is trans, is this way. Consider I do a reverse. Now, this is for both clockwise. If I do a both anti-clockwise, that means I would go further from here down this way. That what is outside, when it goes to this, it will be further down for the atom 4. For this one will be coming up because it's an anti-clockwise, it will come up. So, you can also have the structure written this way. So, in this case, if you write either this structure or this structure, they are correct. What is the relation between these two? Exactly. I asked a relationship between these two. I'm not talking about the ratio of a product what I'm going to get. They are enantiomers. So, okay, if not done in enantiomer selective transformation, this reaction is a diaster selective. What I'm going to say is a trans product or cis product. Either I write this or this, they are for me correct. Okay, sometimes the confusion comes, sir, some book has written this as a product, some book has written as this as a product. Don't worry about it. As long as the relation is trans for this substrate under thermal condition, it is okay. All right. Now the same thing. Under photochemical condition, I supposed to do here. What we did is a con. Here we do. Once again, remember this is a bond which you are going to see. That is an axis which you are going to look at it. So this is going to be a clockwise in one direction, anti-clockwise in other direction, because based on the selection rule, I have a 4-end system. Photochemical, I choose a disrotation. So disrotation represents me that in one end I do a clockwise, other end I do an anti-clockwise. So that would give you, once again, this way the clockwise should come, methyl up here, and this way again up here, because it's an anti-clockwise. Here it's clockwise, here it's an anti-clockwise. I have to rotate this way. So that which is outside would also come up. So the relationship between the methyl group in the product will be cis. If I do both opposite, I would get no. Both I said opposite, not only one of them. Again a cis product, it could be, you can, as I mentioned before, you can either write both up or both below, fine with me. Okay. So this, check with your notebook whether that matches the product what we have written before. Let's take again another example which we have mentioned. This is another example we mentioned. Once again, under thermal condition, we supposed to get here cis product, right? Because a 4N thermal, a con, and that's again has to be, this is an axis if you look at it, both if it is clockwise, right. So once again, this is an inside for the atom which is here, the bottom one, the inside. So when I rotate this way, the methyl will go down. The one which is there, that will also go, no, that also will go down. Okay, this is here, Napa. I am rotating this way. So that means if I rotate this way, the methyl has to go down. This methyl also will go down because of the way we are rotating. Both clockwise it will go down, both anti-clockwise will come up. So we can have either this as written as a product, or when I get narrowed to one board close to the end, my size of the structures are coming small. Okay, so let's look at the same. Under photochemical, it has to be a dis. So which means, once again, look at the axis, and then you say one side clockwise, other side is an anti-clockwise. So which means this methyl has to go down. Here it has to up. Very good. It will be, or otherwise you write this other side, which is again they are the same here in this case. Okay. So you guys said here these are enantiomers, right? What about these two? Sorry? No, what is geometry isomer? Yeah, this is a double bond, this is again cis, these is also cis. What is the relation between these two? These two are same, they are meso compound. For information, okay. It is a meso compound because you have a sigma plane, it's a meso compound. So these two structures are same. I just flip it, I get this. Okay, here also if I flip, I get, but what would happen is this above will go below. This is if I do a seat symmetry here, I will get only these two get exchanged. I cannot go from here to here, right? But if I do reverse it, if I do a C2 axis here, I get this molecule. So these two are iso and identical. Same here, these two are enantiomers, exactly, meso compounds. All right, we look at a next one, then other things also we will see, then we will go to a different examples. We will take an hexatri in a similar way. We will take an, so you need to remember always the limitations, requirements, so that you will be able to get an answers. So now, under thermal condition, it has to be this, louder, okay. So this, because this is 4n plus 2 system. So this refers to, I will have, and this is an axis, exactly, one is a clockwise. If I say this is clockwise and this should be an anti-clockwise, that means this methyl is supposed to come the way I am doing, up, and this methyl will come. There is only two options, doesn't mean you have to alternatively choose it. Okay, so the way I am rotating, the one which is outside will come up, the one outside on the other side will come also up. So the product will be the cis product. Clear? And once again, NN and photochemical condition, I have 4n plus 2, you should choose in Kahn rotation. If that is the case, you are supposed to have both same direction, which means this methyl will come, so, no problem, up. No, I wanted a more response, I was just waiting for a more response, because some of them are keeping quiet. So this should come up, this will go down. So that will be of a trans product. So which I do on both anti-clockwise, I will get an this up, this methyl group will be up, this methyl will be down. So I am not writing that particular option. So let us take an other one which we said is an one side trans and other side cis. In a thermal condition and 4n plus 2, I am supposed to have at this rotation, and once again if I look at this is an axis, one side is a clockwise, other side will be an anti-clockwise, the product, this methyl will go down and this methyl will come, that is all about it. We will be able to write an enough structures based on this. So that will come up, this will go down. Same if you do under photochemical condition, exactly, that is the difference you are going to see, and accordingly, yeah, 4n plus 2 system, right. So this will have, because of Kahn rotation, so I will have either both side clockwise, for example, I would end up getting both below or down here, up here. The way I am rotating, both will be down. The time is running very fast. So this is about and generalizing it, right. So you can extrapolate this to any kind of examples for that matter. Don't need to worry about how big or how small the structure is. However, if you are able to understand the number of electrons involved and the condition what the reaction happening and the stereochemistry how it has to be placed, then you will be able to say how the product formation would occur. We will go to an examples. Let us go with an examples of an 4n system. Then we will go from there, and we will also see an ring opening reactions and ring closing reactions, and all that is possible. Antra and supra and antra reactions, they do not come under electrocyclic reaction. We will see that in the next class when I come with the Diels order reaction. There we will see all these options. Suprafacial and antrafacial reactions, doesn't come under an electrocyclic reaction. Okay, the facial selectivity what we talk about over there. Okay, here also is a kind of facial, but then how the bond is forming, how the rotation is done. Here in electrocyclic reaction, the mode of cycle defined as a con rotation or con rotatory or a dis rotatory. In a simpler form, con or dis. A supra-andra comes for a dis order reaction like a cyclodation reactions, or you can talk about a sigmatropic rearrangement, right? In those cases, you talk about a suprafacial, anterfacial, and how the both the side of the lobes, how are they interacting with them and its coupling partner. So that is a different concept. We'll see on Tuesday. Okay, let's take an examples. We'll see an examples and check at what kind of product which we can get. So now, as I told you, these are all the reversible reaction. Now I have an methyl group and this way, and I am heating this. Tell me what will be my geometry of olefin. What kind of olefin I get at the terminal? Because this is in cyclobutene. As I said, all these reactions are reversible reaction. So previously we were talking about as an butadiene undergoing a ring closure, an electrocyclic ring closure to give you cyclobutene. Now I have given you a substituted cyclobutene as a starting point, and I am saying we are performing a thermal transformation. What would be the stereochemistry of my product? So I would have obviously the product. Once again, if I see, I can kind of push this double bond this way and break this in this manner. Then I would get exactly right. In other words, it's a 2,4 hexadiene. Nomenclature wise, it is not the same. Okay, nomenclature if you see, you start from a carbon to carbon, it will be a 2,4 hexadiene. It is. Okay, it is then because of methyl group presence. If it is IUPAC nomenclature, you can still say butadiene for a conventional use because of the product that you are getting, but it is a substitute version. Now I want to know in both this alkene, the methyl group is going to be exactly both are outside or both going to be inside is my question. This is the one which I am doing. Now how do I see this? So how do I answer this question? Is first thing what you need to see, once again look at the number of electrons involved in the reaction in the starting material. How many electrons are involved? 4, because one sigma bond and one double bond, overall it is 4 electrons which are involved. That means it is a 4n system, and you have a thermal condition. A 4n thermal means what kind of mode of rotation I should do? Con rotation, because reversibility, right? The way it closes, it has to open the same way. So con rotation means now I would see this sigma bond as an axis and then try to perform an what kind of rotation? Con rotation. That means both has to be either both end has to be either clockwise or both end has to be anti-clockwise. So now I can go this way and both clockwise. Then what would happen? The one which is on the top carbon will go away, which means the methyl group will be here. The one which is above will go, what you call it as, and this we call them as an inward movement and outward movement, because this for a diene, this is outside, okay, and this is going inside like this. So this is the product you get. Now you can once again clarify with your example what we have shown, that if you take this as a starting material, you get a cis as a product. Correct? That's all about. So reversible, the stereochemistry does not change. Whatever you start with, you go to the product. Even if you go back, the stereochemistry would remain the same. That is the beauty of a concerted transformations. That's the level of stereospecificity what you are looking at. Okay, so there is a sum and stereo element which is present in your starting material. It is kind of converted into some kind of symmetry element in the product. That's why we call them a stereospecific transformation. Now I am taking a trans and doing a thermal condition again. Once again I have to do. So always you write like this, it's always better. It's a 4n, a con rotation. Now I have two options, right? The both clockwise, right? Both clockwise, what happens? The one which is above will go outwards, outside will go. One is below also will come outside because it's below. It has to go out this way. The one which is above, it also has to go out, right? I have methyl group this way, right? In a cyclobutene. So one which is and on top, it goes in a clockwise this way outside. The one which is bottom clockwise also goes out. So that way I would get this as a product. But what about the other one? So if I do both anti-clockwise, what would happen? Both will come inwards, right? So I would suppose to get this as a product. Generally formation of this, because of steric reasons, are not more favorable than in the other product what you are getting, okay? Because if the both has to come inside, there will be a transition state having an steric repulsion. So this would not be more favored compared to this, which will be more favored. Okay. In other cases, here is no problem. Either side you have an one side inwards and the other side outwards in this case. In this case, both can go out or both can come in. That's where the challenge. Right. We will also look at an example when you look at a substitution wise. So let's look at this case. Let's draw a 6-member ring. Easier. Okay. So now it is cis versus trans, we can look at it. Okay. A cis versus trans and how the reaction would potentially occur or will not occur. Okay. So now if you want to compare, you can also compare with an N5-member ring. And what is the challenge we will see here? Okay, the bottom case you have to really heat at very high temperature. Okay, if you heat more than let's say greater than 450 degrees Celsius, okay, then it gives a product which is an 4+3 7-member ring. So this is this. Once again, what we are going to see, you are going to only push this way to open it. But however, looking at the product, you will realize that this cannot form through a concerted process. That's why it reads in very high energy. You understand now here? This cannot form through a concerted process. Why? Because the number of electrons involved in this 4n. Under thermal condition, what will happen has to be a Kahn rotation, right? 4n and Kahn rotation. If this has to go through a Kahn rotation this way, right, both has to be same direction. Here the one which is both alkyl groups are, the ring substitutions are down because protons are up, right. So here we have seen a simple substitution, right. Here I am doing a connected substitution, that's the only difference, right. There is a methyl group, now those methyl groups are connected with either one carbon or a 2 carbon, now made a ring system. Now if I do this, the one which is below will be coming outward or inward? It should be outward. What about this? This is also this is down. This is basically down. That will come inward. So actually your product is supposed to be this. So how many carbons are there? 1 carbon. This has to be supposed to be this if it is a concerted process. Do you agree? The product what is formed is both the alkenes are Zima. That's why it requires a very high temperature to do this. Okay, it does really open up, but gives a Z product. Both has to be in this case Z. But according to the discussion whatever we had in through an pericyclic way, going through an 4n system, a thermal, a Kahn rotation if you do, I suppose to get one E and one Z as a product. and alkenes, one of them will be Z alkene, other one will be an E alkene. In a 7-membered ring, having an trans alkene, is it geometrically feasible? It is not. You cannot have, at least a minimum is 8-membered ring. Right? Trans octene is one can have. You cannot have below that, you cannot have a trans double bond in an uncyclic system because your angle is 120, you cannot connect them back into one at position. It is not practically possible. So, this is kind of not possible to form. That's why it requires very high temperature. It may not go through a considered process. It may not be, I would say. Right? Because if it is a considered process, I should have gotten this as a product. But same, but when I add in 1 carbon extra, this occurs at even at 250 degrees Celsius, right? But the product is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 is correct. In an 8-member ring, it can kind of accommodate where and one alkene is Z and other alkene is an E. That's a limitation. Okay. If there is a possibility that it can go to both Z, that would probably potentially favorable, or it will form, for example. We can also do a photochemical condition. I am not going to go through a photochemical condition. We can exactly extrapolate that under a photochemical through a disrotatory mode and how you can get the product. So now we look at, there is a selectivity called Tarko selectivity. Have you guys heard of this term? Tarko selectivity? Yes, no? Okay. So Tarko selectivity talks about how the substitutions are oriented when the ring opening reaction happens, whether that's an inward or outward opening. For example, if we talk about this system is more of steric, we don't need to worry about. So as I told you that when you have an CH3 and R group, okay. So this ring opening under, for example, a thermal condition, I am not worried about the other carbon, there is no stereochemistry or no stereochemistry issue in this case. But however, I can have two products where a methyl is outward and R is inward, or R is outward and methyl is inward. This terminology you understand, right? What is inward and outward, right? For this system, in the first case, the methyl has gone out, this of diene. That's why we call them an outward opening. That is. And R has come an inward, which is reverse in this particular case. So if you look at an R, if you refer with respect to ethyl, isopropyl and tertiary butyl, you would realize that this is, in this case, this is 68% to 32%, and in the tertiary butyl when you go, it will be just opposite versus 68. Exactly, purely a steric driven, there is no issue. When you are comparing between a methyl and then R group, when you keep increasing a substitution, right, what you see here, the bulk is increased. That means the bulky substitution prefers to stay outside. When there is an option to go both the direction, it prefers to stay outwards. Of course, there is some amount of an inward is there. That's at level of masters, right? At the bachelor's or the school, we will say that, okay, this is a major product, we are done with that. But actually, it is not true. When you go and start understanding, there are major products, there are minor products. There are other possibilities also, right? So, this case, you will realize that it gets switched from ethyl to tertiary butyl when you go, it just opposite forms, just purely steric. But however, this is more prominent when you have an substitution with an electron donating group, which is mesomerically electron donating group or mesomeric electron withdrawing group. It could be aldehyde, esters, amides, any of these systems, or you look at an OME and this kind of systems, which are, this is an mesomerically electron donating. It's through resonance or mesomer, the pair of electron can get shared. It's a donating group. Here, it is kind of a withdrawing group. So it is very interesting. is that this is what we classify as the selectivity. When you heat, the product what you get exclusively is this. So, electron donating group, a mesomeric electron donating group prefers to be outwards. Okay, outwards movement is preferred. When you go for an electron withdrawing of this type, the inward movement is preferred. This is what is called as a selectivity. This model was kind of proposed by Professor Ken Houck. For the selectivity is what is observed, right? They say that there is a secondary orbital interaction which gives you an such an observation. That selectivity is called selectivity. Okay, so please remember that when you have an electron, mesomerically electron donating substitution, it prefers to exactly go out. When you have an electron withdrawing substitution, it comes to an inward. The beauty of this transformation is I can redraw this aldehyde in this particular manner. What would happen? Now, how do you consider this system? It's okay, you have an heteroatom, that's not a problem. But based on electrocyclic ring closure, what I talked about, this is also still a kind of a conjugated polyene. But only thing is, one of the carbon is replaced with an oxygen. Now I have 1, 2 and 3. How many say double bonds? 3 double bonds. How many electrons? 6 electrons. 4n plus 2. We can still have an electrocyclic ring closure to give you a product like this. It won't stop here. It can further go to this. So initially it is a 4n electrocyclic ring opening followed by 4n plus 2 ring closure. This means if at all you wanted to say the 4n thermal, it has to be con, and here 4n plus 2, it should be this. Luckily, we do not have substitution, so we are not worried about the stereochemistry here. Of course, oxygen involvement, so you have only 2 lone pairs, you don't need to worry about which stereochemistry you are getting it. So let's look at another interesting example. So this is a selectivity. This is substitution dependent, but it has various advantages when you are looking at an appropriate substitution when you are placing it. So let's take this system. It is not an exactly a cyclobutene. And this is a benzo-fused version. The benzo-fused version, benzo-cyclobutane, what you call it, butene, right? So now, can this undergo an electrocyclic ring opening or not? Is the question when you heat it. Thus, this molecule has a kind of an functional groups which undergoes an electrocyclic ring opening. Does it has or no? How? If you consider alone this, do you think that double bond I have drawn it this side or you want to draw it this way? I have no problem. They are the same. Okay. If you think that then double bond has to replace this side, not this side, it's all the same for me. If you now you see it, now you can see that. Now this, if you ignore this point, this is a cyclobutene. This can undergo a reaction under thermal or a photochemical to give this as a product, which is it's a ring opened and bismethylidine of an orthoquinone methyl. It's not an orthoquinone, it's a bismethylidine of an orthoquinone. You have both orthoquinone means you have oxygen, it's are converted to now an alkene, right? This is a carbon-carbon addition. This is beautiful substrate for a cycloaddition reaction. Consider that I have an electron deficient tetracyanoethylene. I can create the molecule which is this. This is a beautiful thing. So this isn't because it was aromatic, it lost aromatic, it gains an aromatic. So it is again interesting if you have a substitutions. So now I am not drawing a double bond outside, I will prefer to draw a benzene this way, right. I have a phenyl. Now tell me where it will go if I do a thermal reaction. Or you want to have photochemical? No problem. Let's take a photochemical because we have not seen a photochemical reaction. So one has to be, it has to be 4N system, right? Mode of opening has to be this. So this means one has to be a clockwise, another has to be anti-clockwise. Either it both has to come in, both has to go out. Which will be favored? Both going has to be out, will be favored. So you would have this as a product. And once again, if you react this with an tetracyanoethylene, you would end up getting this as a product through endoselectivity, which you will see in next class. And the same way, what will be my product? Extending a Tarko selectivity here, if I heat, because of methoxy, it has to be outside. This will be the product what you get. What about this here? It was an inward movement, so that should give as product like this. This should lead to a further cyclization. Yeah, not 4n+2, 4n+2 type cyclization. The 4n+2 number of electrons are involved. It should be a disrotation, and again a thermal, for example, in this case, can give a product which is this. I will take 2 examples and then close. It's already 1 o'clock. Okay. So this we told about previously. Depend on the system. If you choose a condition variate, you get a different product. This is beauty. If you use either photochemical or thermal, it gives the same product. How do we explain this? Cyclooctatetraene, when you heat or under photochemical, both thermal or photochemical, irrespective of the condition, it gives only this product. How do we rationalize this? Any answer? Based on the discussion whatever we had? Depends on how the product is formed, right? The both case, it depends on the HOMO or LUMO. If the cis product has to form like this from a cyclic system, the mode of cyclization has to be always disrotatory. Remember, okay? Only through disrotatory mode for a cyclic system, you will get a cis ring fusion. Understand? Consider that these two are occurring this way, right? if this has to come up, both the proton which are outside has to come up, for example, I have to do an anti-clockwise, clockwise here and anti-clockwise here, or on vice versa, right? And one side, if it is clockwise, on the other side, it's an anti-clockwise. So if I do a clockwise, then only the proton which is outside will come up. The proton which is outside, in this case, will also come up. So only through a disrotatory mode of ring closure, we can have a cis ring fusion in any case. That is you can completely close your eyes and then go ahead. You will not have a cis ring fusion through a Kahn rotation. For a cyclic system, don't connect to something else. I am talking about a cyclic system. But why a cyclooctatetraene gives only one product, both under thermal as well product? Because you cannot have a trans ring fusion with a 6 and 4. Quite strained system. It's not practical, right? Geometrically, it's not a allowed, stable structure what you're talking about, right? So, the disrotation means, so this molecule kind of behaves very differently. So, what does this mean? Under the photochemical condition, this molecule reacts like a 4N system. Under thermal condition, it reacts like an 4N plus 2 system. If it is a 4N this way, when I say, I get this product, right? So, I can also redraw this structure. I can also redraw the structure such that now I close a ring here, a 4N system, photochemical. This is a 6 system, 4N plus 2 system, thermal we have seen that. Now, for a 4N system photochemical, let's look at this example, right? So, now these are the carbon which are going to connect. So, disrotation has to be, is coming from this side. So, this is an anti-clockwise and here it's clockwise. That would give us again a same product. So, that is the beauty within a cyclooctatetraene. Either you look at a thermal condition or a photochemical condition, it results to the same product because of the stability what you are looking at the product. Both the case, only through disrotation the reaction occurs. The molecule tend to choose itself either to go through an 4N plus 2 type or a 4N type reaction. So, we have one more example before I close, which is also interesting, but then the product is not same, the product is different. So, let us take a 9-member ring. Okay, this is a 9-member ring with a nitrogen. So, now going through the same funda, what would be my product if I heat? What would be my product when I do a light? So, which means the thermal case, you would probably prefer obviously in both the cases dis, because the ring fusion you wanted to have a cis-in relation. So, it has to be disrotation. So, if that is the case, here it is dis and here also if it is dis, if you want to have, it should be 4N plus 2 electrons has to involve. Here it is 4N has to involve. So, out of this, whatever way we do a 4N plus 2, that means out of these 4 double bonds, you can have either 1, 2, 3 or 1, 2, 3, either way, right? Either this carbon and this carbon can connect, or you can look at this carbon and this carbon connect, you will have a 6-member ring. So, now let us look at an carbon, this and this connecting. At this rotation, this can up and this can come up. I can have a product which is a dihydroindole type. If it is a 4N plus 2. Now, when a photochemical condition, it is a 4N. Now, you can have all these 4 double bonds getting involved, can result as this way. Once again, I can do these two, that can give as a product which is an 8-member ring. So one could potentially ask, sir, why are we interacting always at the terminal? Why not at an internal double bonds itself? Consider that, why should I interact these two? Why not between these two? That also I can do, no? Why am I interacting always at the terminal lobes? So if you look at in conjugated polyenes, right, the orbital coefficient, size of the orbital coefficients generally are larger at the terminal carbons. So this is what we classify as a periselectivity. Okay, so those interactions are always more favored compared to the one which you are looking at an internal double bonds. If there is a possibility, it always tend to react at then a terminal one. Like the ones here, it's all completely conjugated. Here you don't apply that panda here. But in this kind of systems, one could potentially see that where the terminal ones tend to react better over an internal double bond. There are situations where inter double bond reacts. Again, it's a condition dependent. For example, if you take an this molecule, I'm sorry, I'm taking more time. I'll just stop here. Say, if I take this molecule, okay, if I do a photochemical reaction, what kind of products I get is, it depends. I can, because a photochemical means, exactly right, 4n plus 2, this will happen because 6 double bonds are there. If 4n plus 2, when I do a photochemical, it is a con rotation, the ring junction will be trans. So that is not going to favor. So then you choose a 4n system. Where do you choose and how do you choose also matters. Because when you have an electron donating group, the HOMO rises. Okay, in this case, you selectively get this as a product. In a disorder reaction, when you guys studied, you would have studied about an electronic effects, right? Normal disorder and inverse disorder reactions. You guys heard of this? No, then we will discuss in the next class. Okay, in there you will talk about when you have an Y and dienes are generally electron rich, dienophiles are generally electron poor, because you want to bring down the gap between an HOMO and LUMO. So when you introduce an electron donating group, the HOMO energy increases. When you put an electron withdrawing group, and any molecular orbital for that matter, it need not be HOMO and LUMO, right? In any molecular orbital, when you put an electron substitution, donating substitution, the energy rises, reactivity increases. When you put an electron withdrawing substitution, it decreases basically. The same way, if you look at it, this diene, because this is not conjugated by through this OMe. This double bond is kind of isolated for this OMe because the resonance can only go through this. It cannot go here. So it's only this is kind of an rich. That's why you get kind of only this product, not this way. This way doesn't occur. Right? There are lots of examples for an electrocyclic enclosure. I actually, if in the next class, I will not take you guys directly to this reaction. There is some interesting example in an electrocyclic enclosure itself, where this is only we have looked at in 4 atom systems, butadienes and the cyclobutene systems. We can go to an cyclohexadiene with the substitutions. We can go to an even in higher analogs, like an 8 carbon system. We can go to an, instead of an even number, you can go to an odd number, where reactions are very interesting. There is something called neserocyclization. There are some cyclopropane ring opening, which are very stereospecific in nature, at a condition what we do. So those probably I'll touch upon and then take you guys to an cyclodation probably on Tuesday. Okay, I'll stop here.
SwayamPrabha, Digital India, Educated India.